Units for magnetic field, Tesla. Capital T. And the Tesla is our SI unit for magnetic field, but it's a fairly large quantity. People that work with magnetic fields a lot, they get tired of writing 10 to the minus 3, 10 to the minus 4, 10 to the minus 5 every time. So they use Gauss. 1 Gauss is 10 to the minus 4 Tesla, right? Like we saw that in lab the other day, right? So Gauss is another common unit you see for a magnetic field, but we use Tesla. Huh. I would just say Gauss. Just like I would just say Tesla for if I had a 6 Tesla field, right? I wouldn't say Teslas. Or a 6 Newton force, right? You don't typically pluralize the units. Okay. And this is dependent on Q, right? And then Q does flip the direction. And the reason is, I mentioned it the other day, it's a cross product. The force, if you want to write it as a vector equation, the force is equal to Q V cross B. So a cross product between two vectors, V and B, yields a vector that's perpendicular to both of them. And the order is very important, right? This is V cross B is not the same as B cross V. It flips it by 180 degrees, right? They're in different directions. So let me give you a little example here. If this is V and this is B, right? What direction would V cross B be? Using your right-hand rule, V cross B would be out of the page, right? But what direction would B cross V be? Into the page. V cross B is out of the page. B cross V into the page. You get the same magnitude, but opposite directions. So they're not the same. The order is important here. The force is V cross B. And Q, if Q is positive, the force is just given by the direction of V cross B. If Q is negative, then it flips it by 180 degrees. So you can see mathematically how it works. And one way we can write the cross product in the magnitude, to get the magnitude, is this VB sine theta is the magnitude of V cross B. Okay? So one thing I wanted to show you, we talked about the fact that we can visualize magnetic fields now, and I got the iron filings out, right? And we sprinkled them all around the bar magnets, and we got to see that. But what I've got here, that's still 2 dimensions. What I've got here, this is kind of fun, is a 3-dimensional object. Let's see how this is going to work. This may not work. So there's a slot down the center where you can slide a magnet in there. And we've got these iron filings now that are in 3 dimensions. I'm trying to keep it. You can sort of see it taking the shape, can't you? Of the fields, of the magnetic field lines. But so this looks just like it did in 2 dimensions. But if you hold it up and look at it yourself, you can see the field lines forming sort of in 3 dimensions here. So I'll pass it around. But be careful, the magnet, the bar magnet, slides in a hole in the top. And if you're moving it around, it's going to fall out. And you can see it's already broken once. So we don't want it to break anymore. So kind of keep your finger over the top where the magnet goes. And if you need to shake it up a little bit and mix up, or you can take the magnet out and give it a shake and then look at it. But I think it's kind of neat to see how those align themselves with the field in this viscous fluid in 3 dimensions. One is in something called a velocity selector. So oftentimes you are creating particles that are charged and accelerating them across a potential difference, so they should have a certain speed. But what typically happens is you get a range of speeds. Some of the particles are accelerated across the entire potential difference, some are less. So it's you get sort of a range of speeds coming out. So you have a section here where you have particles coming out, and you're hoping that the charged particles are coming out with a certain speed, but chances are there's a range of speeds. And what you do is you run them through a magnetic field and an electric field. So you have like a sort of almost a capacitor. That creates an electric field in one direction. That's our E field. And then you'd have a magnetic field. I'll do mine in blue, I guess. In another direction, maybe into the page.